some results that we actually have in the lab. I'm not going to show you raw spectra. By all means, I'm happy to email them over to people. We have an application note written about this that has the spectra in it. And as I say, I'll be more than happy to talk about it, but I'm going to go on to what we do with that information. So this is a qualitative measurement. This is called a scores plot. So for those who are familiar with chemometrics, this is a principal component analysis. What we basically do is we pull out the information. So PC1 is the biggest piece of information that's actually present in the spectra we see. PC2 is the second biggest piece of information. PC3 would be the third biggest, and so on. And then this number down here tells us how much of that variation is captured by that. So 86% of all the change we see in our spectra is captured by PC1. The next 10% is captured by PC2. Add those two together and you've got 96. That's a huge amount of your variation already captured. And in this sample, we were looking at different types of oil and adulterated oils. Now, I appreciate adulterated oils for oil refining may well not be a problem, but it's a good example of showing the types of things that you can pull out with mid-infrared. And you've probably seen similar graphs to this with near-infrared, because this is a classic go-to that someone wants to demonstrate their near-infrared. So we thought we'd start there too. So down here, we've got pure soybean oil. Up here, we have pure canola oil. And unsurprisingly, in between the two of them, we have a canola and soybean oil mix, because it does literally say, well, you've got features of both, we sit in the middle. And then we have different types. We have pure olive oil here. We've started to adulterate our olive oil with canola oil, and that's why it's drifted up towards the canola oil. And then we have olive oil that's been adulterated with soybean, and unsurprisingly, it starts to drift down towards the soybean oil. Computers can pull this out and statistically generate a likelihood as what type of oil that is, as well as telling you how much adulteration there is. So you can do that on real time and update every minute or 2 minutes of a continual pipeline if required. As I said, I appreciate for refining that may well not be terribly useful, but this is the kind of information that could happen towards the back end of a process to check you're within specification qualitatively as well as quantitatively. And I should point out that spectroscopy, all types of spectrometers, can run multiple calibrations at the same time. So you can have a calibration that looks for something qualitatively whilst also making a quantitative measurement at the same time with one instrument. We then went on to look at some quantitative measurements. So this is free fatty acid and fatty acid methyl esters dissolved in sunflower oil. So again, this is laboratory conditions. I appreciate these are effectively ideal conditions from clean samples. But we dissolved both FAMEs and FFAs in the same mixture. So they're both present at once, and there are lots of different types. I cannot remember off the top of my head how many FFAs and FAMEs there are, but I think there are at least 6 of each. So we've got things like linoleic, oleic, linolenic, palmitic acids present, and their FAME equivalents. And for this, we managed to build calibrations with a typical error, which is effectively our limit of detection of 0.24% for FFA and 0.06% for FAME within this concentration range. The errors are partially to do with the concentration ranges that you look at. So if you only look at lower concentrations, you tend to get a lower error. If you look at higher concentrations, you tend to get a higher error. But that's just statistics. That's the way that these models work. But I hope you'll agree these results are actually pretty good and encouraging enough to move on to something like a plant trial, which is what one of our customers did. And they very graciously let us use their data to share with you what they've managed to achieve. So these are results from an oil refinery. The instrument is installed quite far downstream. This is actually right towards the end, just before the packaging step. And that's simply because it's an easy place for them to install the instrument as a proof of concept. After having seen these results, they've decided to move the instrument right upstream before the caustic, the lye mixing, so that they can actually control that based on a real-time FFA measurement. So they were so pleased with it, they have moved it upstream, or are doing so as we speak. We're trying to wait until they can get contractors back on site because coronavirus has caused problems for absolutely everyone. So in these results, these are actual samples taken from online. So we were installed online for continuous measurements, and this is the calibration. So for FFA, in lots of different oil types, you may be asking yourself, or thinking, yes, but do I have to have a calibration for every oil? This refinery processes at least 2, if not 3 or 4 different types of oil, and we've built one calibration for that, regardless whether it's sunflower, whether it's canola, whether it's high oleic, low oleic. It's one calibration for all of them. And in this case, the limit of detection was 0.083. So you can see that's improved on before because we're looking at the lower concentrations. We also managed to see chlorophyll. Now, I was actually quite surprised by this because these numbers are low, less than 1 ppm. These are extremely low values for spectroscopy, but we managed to pull out a calibration. We then ran this calibration in real time and looked at, it was something like 4 weeks worth of data, which is what I've got here. So we've got the instrument was installed halfway through February and left online until halfway through March. And for the FFA measurements, we can basically see they were trying to hit for a 0.1% specification, and the vast majority of time we're within that. But not long after installing the instrument, they drifted outside of specification. And this gap here is approximately 12 hours. And it was 12 hours before they took their offline sample, analyzed it, and realized they were outside of spec, and then did something about it. And they overcompensated. Now, this may have been deliberate, it may have been accidental, but they overcompensated for it. And it was another 6 hours or so before they took a reference point, and then they start to drift back up again. With online real technology, real-time measurements, they would have known about the fact that they were drifting outside of specification there. The second it started to happen, we have updated these spectra every 2 minutes. So every 2 minutes you get a measurement. You might want to wait for 7 measurements. Statistical process control tells you that's a good time to wait to see if you're outside of process control boundaries. So 7 measurements, 2 minutes per measurement, that's 14 minutes compared to 12 hours, at which point you can do something about it. And you can then feed that result forward through to your dosing control, and you can adjust it and maintain much, much better control. So you use less chemical, which is cheaper. You don't go outside of specification, so you never have to worry about throwing away any batch, and you have much better control over everything. You can then also use that for things like controlling centrifuges to make sure that you're not throwing away oil in your water stream, or that you have no water in your oil stream. The possibilities are quite exciting. The chlorophyll measurements they're okay, they're reasonable. I stress again, we're below 1 ppm, so I'm impressed myself that this works at this kind of detection limits. They're more for trends, I think. If you had a spike of chlorophyll or something weird had happened and there was a huge amount of chlorophyll contamination, you would spot it. But within this number, it's more for a trend than fine control at this type of value. So what else is in our pipeline? Phosphoric acid dosing. I'm aware that that is another area of interest. Infrared should not directly be able to measure metal ions, but we believe from previous experiments in other technologies, think we can see the effect that the metal ions have on the spectra of the phospholipids themselves and the any free fatty acids that may be chelated to them as well. So we've got some samples actually arriving from a customer very soon where we're going to start building calibration on that. Trying to build lab samples of phospholipids and metals in oil is not even worth trying. It's too difficult to do. This is much more sensible to do with real life process samples. So we are expecting those imminently, and we will work on them and publish an application note as soon as we're able to. The other thing we can do is measure things like properties. Iodine value, which I know is effectively the degree of unsaturation within your process. We've just finished doing our proof of concept work on that, where we bought a variety of pure triglycerides with known iodine values. And from that, we were able to give an error of ±4 on the iodine value, ranging from 0 up to, I think, 260 was the highest number that we got. And again, we'll write that up and publish that available for dissemination as soon as we've done it. But I throw the question to yourselves. If there are things you'd like to measure, we're more than happy to do it. We've got a laboratory, we've got instruments, we can take samples. We would love to look at your samples for you and actually get some meaningful data for you and hopefully start a relationship. So, conclusions. We are at the point where closed loop control and real-time process optimization for complicated processes is realistically within reach, but it does require things like spectroscopic measurements. And people are beginning to roll this out, and they're making real efficiency savings, game-changing efficiency savings. And it's a really exciting time to be involved in this. The use of robust FTIR instruments allows for the control of chemicals in refining. We know about it in loads of different industries because I'm lucky enough to work in lots of different industries, but we have now beginning to get the impetus, the movement here to roll this out into things like seed oil refining. And the key difference is that the static optics of the IRmadillo allows you to bring the information rich from the FTIR out of the laboratory and into an industrial setting. Thank you very much for listening, and I'm very happy to take questions.